Imagine for a moment that you find yourself facing an impassable wall. You do not have the energy to climb it, you do not have the tools to bring it down. In classical physics, the one that governs the world we see every day, you would be stuck. Yet in the quantum world, you could literally pass through it, like a ghost walking through walls. This is not fantasy, but scientific reality demonstrated. And on October 7, 2025, 3 scientists received the prize for having shown that this seemingly impossible phenomenon does not concern only invisible microscopic particles, but can also involve macroscopic systems that we can build and manipulate in the laboratory. I am talking about John Clarke, Michel Devoret, and John Martinis, a revolutionary discovery of the macroscopic quantum tunneling effect. Today, I will take you on a journey through one of the most important discoveries in recent years, a discovery that is changing the way we conceive reality and that has opened the way to the quantum technologies of the future. Before we begin, if you have not done so yet, I warmly invite you to subscribe to the channel and to enable the notification bell so you won't miss any of our scientific deep dives. To truly understand the importance of this prize, we must start from the basics. We need to understand what the tunneling effect is and why it is so astonishing. Imagine an electron confined in a potential well. Classically, if the electron does not have enough energy, it cannot escape. In quantum mechanics, however, the behavior is different. The electron's wave function extends beyond the well. There is a finite probability that the electron can be found on the other side of the barrier. This is quantum tunneling. It is the same phenomenon that powers devices such as the tunnel diode and is essential in nuclear fusion inside stars. Quantum tunneling shows that the rules for small scales are different from our everyday intuition. But what if quantum tunneling could happen not only with single particles, but with collective states of many particles? What if the entire state of a system could tunnel? This is the question that researchers like Clarke, Devoret, and Martinis investigated. They built circuits where macroscopic variables behave quantum mechanically. These are superconducting circuits that include Josephson junctions. A Josephson junction is formed by 2 superconductors separated by a thin insulating layer. Classically, electrons should not be able to cross that insulator. Quantum mechanically, they can do so via tunneling. The key point is that the current in such circuits can be described by a single macroscopic wave function. The current can flow clockwise or counterclockwise, and these 2 possibilities can form a quantum superposition. This is not the motion of individual electrons, but a collective quantum state composed of billions of electrons acting as a single quantum entity. At very low temperatures, the quantum behavior of the whole system becomes dominant. Clarke and his collaborators built circuits with these junctions and cooled them to temperatures close to absolute zero. What they observed was extraordinary. The current in the circuit could exist in 2 states, flowing clockwise or flowing counterclockwise. And the system could tunnel between those 2 states. This is macroscopic quantum tunneling. The fact that a collective variable describing a macroscopic current can behave quantum mechanically was revolutionary. It told us that quantum mechanics does not belong only to the microscopic world. These experiments also underpin the development of superconducting qubits for quantum computers. A qubit can be encoded in these 2 current states. By controlling and reading out these states, we can perform quantum logic. But there are also fundamental questions at stake. If macroscopic variables can show quantum behavior, where does the boundary between quantum and classical lie? What defines the transition from the quantum superposition to a single definite outcome? These are the same questions at the heart of interpretations of quantum mechanics. They connect to debates about measurement, decoherence, and possible objective reduction mechanisms. To study these phenomena, researchers look at coherence times, environmental coupling, and theme mechanisms that cause decoherence. They design experiments to isolate the system as much as possible from noise and uncontrolled interactions. The better the isolation, the longer the coherence can be preserved. Long coherence allows richer quantum phenomena to be observed at larger scales. Another striking example of quantum behavior on large scales comes from superconductivity itself. In a superconductor, electrons pair up into Cooper pairs. These Cooper pairs condense into a coherent quantum state described by a single wave function. The current can flow through a superconductor without any energy dissipation, theoretically forever. But there is something even more extraordinary happening in a superconductor. Electrons no longer move as individual particles. They pair up 2 by 2, forming what are called Cooper pairs. And these Cooper pairs behave as a single collective quantum entity, as if all electrons in the superconductor formed a single wave function that extends throughout the entire material. This is a quantum behavior, but it happens in a system that contains billions of particles. We are beginning to see quantum mechanics manifest on scales approaching the macroscopic. Josephson junctions are critical points in these circuits. They are thin insulating layers that separate two superconductors. Classically, electrons should not be able to cross this insulator. Quantum mechanically, they can do so via tunneling. And here comes the crucial point. We are not talking about single electrons tunneling. We are talking about Cooper pairs, electric currents that behave collectively like a single quantum entity. Clarke and his collaborators built circuits with Josephson junctions and cooled them to temperatures near absolute zero. At these temperatures, the quantum behavior of the system becomes dominant. And what they observed was extraordinary. The current in the circuit could exist in two states, flowing clockwise or counterclockwise. The system could be in a superposition of these two states and could tunnel between them. This is the macroscopic manifestation of quantum tunneling. The discovery has both fundamental and technological implications. On the one hand, it challenges our notions of where the quantum world ends and the classical world begins. On the other hand, it provides the physical basis for superconducting quantum technologies. These experiments have shown that quantum mechanics can govern the dynamics of systems that are large compared to atomic scales. They force us to rethink the frontier between quantum and classical physics. They also remind us of the importance of low temperatures and meticulous experimental control. Only under those conditions do collective quantum phenomena emerge clearly. If you want to explore further, there are many reviews and papers that dive into the theoretical and experimental details. But the essential idea is simple and profound. Quantum mechanics can manifest at scales much larger than we once thought possible. If your interest is in applications, note that superconducting circuits are among the leading platforms for quantum computing. They offer scalability and strong control, which are essential for building larger quantum processors. They also require very precise engineering and shielding from noise. Building a quantum computer is not only about demonstrating quantum effects, it is about stabilizing and controlling them at scale. This requires expertise in materials, cryogenics, microwave engineering, and quantum control. Returning to foundational questions, these experiments are a fertile ground for investigating decoherence. They allow us to test models of how quantum superpositions degrade in realistic settings. They also allow us to probe whether there are any deviations from standard quantum mechanics at larger scales. So far, standard quantum mechanics has held up well under experimental scrutiny. But the search continues, and new experiments push the limits further. Another angle is the interplay between quantum mechanics and gravity. Some theoretical proposals suggest that gravitational effects might play a role in the collapse of the wave function. To date, these ideas remain speculative and extremely difficult to test. Nevertheless, experiments that extend quantum behavior to larger masses and spatial scales help put constraints on such hypotheses. They probe realms where potential new physics might emerge. In recent years, experimental techniques have improved dramatically. Control over materials, fabrication, and readout has made it possible to create cleaner and more coherent systems. This progress is why we can now observe quantum phenomena in systems that were unimaginable a few decades ago. But the experiments are delicate. They require patience, ingenuity, and precise control of many parameters. They also require the collaborative effort of theory and experiment. Both are necessary to interpret results and design better tests. Science advances through this cycle of hypothesis, test, and refinement. These discoveries are an example of how fundamental research can lead to unexpected technological revolutions. What started as curiosity about quantum weirdness now underpins an entire field of quantum engineering. If you enjoy this kind of content, your support helps make it possible. Your support makes all this possible. Subscribe to the channel. To truly grasp the importance of these results, one must understand the basic concepts of quantum mechanics: probability amplitudes, superposition, and entanglement. In the quantum world, particles do not have definite properties until they are measured. They exist in superpositions of states. They are intrinsically probabilistic, and they can exhibit phenomena such as entanglement, where particles can be correlated in ways that defy our classical intuition. And now we know that these phenomena are not limited to the invisible microscopic world. They can manifest in systems that, while still small compared to human scale, are enormous relative to atomic scales. And this opens fascinating questions. How far can this scale extend? Could we ever observe quantum effects in truly larger objects? Could we ever put an object visible to the naked eye into a quantum superposition? Some experiments are trying to do exactly that. They are attempting to create quantum superpositions of increasingly large mesoscopic objects, complex molecules, nanoparticles, and perhaps one day even microscopically visible objects. These studies also have implications for our understanding of space and time. In quantum mechanics, space and time are treated differently than in Einstein's general relativity. Reconciling these two frameworks remains one of the great challenges of physics. Pushing the quantum classical boundary experimentally provides valuable data that can inform theoretical work. It helps narrow down which theoretical paths are viable. Ultimately, experiments of this kind deepen our knowledge and expand the domain where quantum theory has been tested. They remind us that nature often resists simple categorization. We are still learning where the boundaries lie. There will be unexpected surprises along the way. Science is a process of exploration and incremental discovery. The story of macroscopic quantum tunneling is one of those stories that bridge foundational physics and applied technology. It shows how deep curiosity about the laws of nature can lead to new tools and new possibilities. Thank you for following this long, deep dive to the end. The universe is full of wonders, waiting only to be discovered.